You can start working on the assignment now. And if you have questions, so let's try in the next 10 minutes to finish the tank sizing. After 10 minutes, we start with step 3. Okay? Yes, we are now calculate T2, T3, and the mass of the tank. So how about you get the oversupply that happen now? Fix that first. But what positive and then separate positive values, negative values, positive values, negative values. Change the design.
This one again. 70 something. Yep. Anything I want? Sketch. First, you tell me all this, right? Yes, this apply but kg per second. Yeah, so you increase time to continue up and so you want to supply your kg per second. Multiply kg per minute. Multiply by the so you change the effect. Beside the kg,
the T2 or 0. Yeah, I think it's 20. It's 0 plus 20 probably. Should be the same as T1. There's no difference. Oh yeah. Oh, he didn't use the volume flow or the cooler, he used the supply water. Use the water supplies. Water supply. Water flow rate. No, this one. Use this one divided by 60 plus 20.
So I've written both these equations on the board. Try them out with the second exhaust out. Does it make sense?
The Q coolant is which value?
Q coolant is on the Excel you see at the front, column M.
The thermal energy.
Yeah. So, have you used that? Okay. That's right. Yep. 85 minus 82. Yeah. Then there should be one more bracket. Before I, add a fraction. Yeah, one more at the end, right at the end. 1.005. Are you using 1.003? Yes, no, they should not. This one. No. Yeah, click on that.
Exhausting.
Where's your T2? No. If you're using CP in kilojoules, no. Are you using what's the value of CP? Yeah, that's in kilojoules. Kilojoules per kilogram. Joules will be 4,186.
Oh, okay, okay.
The second part of it, second half of minus sign. Everything else is 4.5. So everything is compromised. What is this? What is No, it should be citation. So let's check that. Let's go back to very show me what can you double where is that? The go how many are there? B7. Oh, there's one missing. Is there a 4? How many columns KW are there? 1, 2, 3, 4. These are so that's B in there, D in you're missing B. There's another B in there, D in C.
I think to change to liter per day is times density.
Yours is okay.
Density
Yours might be okay.
is kg per
one
liter.
column.
Density is what?
So your one is generated for
Density per. This is water basically of kg per liter cube. So
no, it's not changing.
kg per day. Answer
You
kg.
selected 16.
Density of water. Divide should be divide by density to be
Just delete that out B. It was just a check for us.
oh yeah, okay. This is flow rate. Flow rate divided by density is volume. Yeah, then should be
If you're getting your T exhaust, that temperature, negative values, because we found one of your classmates made a silly mistake. I think I would share that with others so others won't make that same mistake. If you're getting negative, that value, definitely you're missing 1 kW from the original table. When you added the total electrical power. So I want everyone to go to your tables, total electrical power, column, total electrical power column.
Oh, I think it missed out one. My first time also.
Yeah, total electrical demand, that column, and see if there are 4 things you are adding, 4 cells, not 3. Check that for your own. Are you adding 4? C, E, F, H, or whatever that. Anyone who is doing 3, that's a mistake. 4, everyone? Okay, so I think you should get this positive.
9, 6, 9, 5.
Thanks for making that mistake. So no one else makes that mistake again.
The 977 is the density. So you get this one is volume flow rate.
Yeah, but then this one is at
kg per day. So if you change day to hours, it's 24 hours.
Someone asking me a question then.
So
because 1 kg is 1 liter.
yeah, 1 kg.
At least at 20 degrees Celsius. So the one is supposed to find at 30, 85 degrees Celsius. The weight at 85 degrees Celsius.
Then I wait for it.
This one can exhaust up, fine. Exhaust up.
Yeah, fine.
So fast.
Yeah, exhaust out.
Mesh flow rate, exhaust is the same, right?
Mass flow rate of that one is mass flow exhaust for exhaust kg per second. So you have this one, you don't need to divide by 16 because per second already. You just times C.
Which is what is mass flow for exhaust.
Yeah, the mass flow for exhaust.
Yeah. 60, right?
Times 1.005. You don't need to divide by 60 because already kg per second. What are you doing now?
So can you show the formula?
Yeah.
U5 water supply.
Yeah, 60. That's more.
One 85 minus S5 is equal to, and not correct. Right, right.
That's okay. Make sure temperature of exhaust is greater than 110 degrees Celsius. It must be greater than 100 or equal. Equal to greater. That's why you started with something else. Should be greater than 100. That's right. But go to Kelvin.
The gauge is 45, right? So it is multiply by 4.18, multiply by our change in temperature, which is 85 square. Okay. Then you get the total heating demand, which is kW.
So what is that? What you use? That's 5 plus. Question is wrong. No, not demand, not demand. Supply. For second. Yeah, that's like original temperature. I feel it's very
Fine.
Yeah, the weather is very
Storage. Surface area, heat loss, heat flux. No, I said how to buy.
Mine my kg per second.
What's that?
81 minus y.
No, at least I think it's a curve. Curve. You can do this, if you can do this. Chat. If you can do this.
Yeah, this one. Supply and one for hot water.
I don't know whether it's applicable. I don't know whether it's applicable in the question. Okay, just do it.
I think okay lah, this one should be fine.
You
go to the total electrical power each hour, right? The speed. Well, one higher. Maybe 2 dB minus 21. Yeah. So you use the 21, right? Then, okay. Then you.
I think 3 is 81.
You create a new sheet.
I think guess.
You calculate the example.
Then you do this. Okay, basically, right, you need to go to the table. This is the question. Then you need to key the electrical power for each node. So you see the load, then you go to 21. Then you see the yeah. So you need to write down for each one electrical power. So let's say 21 is 100%, right? You just interpolate it. Then you need to write down the fuel consumption for each, like, for each percentage. Then each coolant is, you need to interpolate.
Can you move right? What is V5?
Yeah, we just said you.
And what is W?
Like I said, you know, like, you can see the formula. But the values don't copy because like, it shows the different variable. We also have to get
So what is O?
mine is following 60.
You don't need. What's your teacher?
You basically the graph function, you don't need to then just put any of these graphs. But then you need to come up with this equation.
Can you check
This equation,
W curve?
you need to put two
For that.
graphs. One is for y, so then one is for coolant. So one is then the other one is
Let's go now.
or using this.
Electrical, total electrical.
Yeah,
I think the method a bit different. So this in
except for the 100% one is already given to the
Okay, everyone finished? So, have you calculated the volume? No? T2 is there, right? And exhaust temperature? You got it? No? Exhaust temperature. You're not getting it? Okay. So, volume. Have you found the diameter? Read the question. Everyone, I want you to read the question, that part which asks you calculate the diameter of the tank, size of the tank. This one, 85 minus 50. Is it 57 or is 7? Okay, 7. That's good. What is M? Oh, that's very small. So that's wrong. Yeah. That's wrong. Mass flow rate of exhaust is wrong. Here, it should be 0.03, not 0.01. Let's go to catch.
you need to read the question and
That's
tell me your idea.
1.7. So how you get 1.9? Like at 100%, it should be 4.7. Exhaust. That should be 4.7. Everything will be use that equation. Why did you use that one? Okay, everyone is now comfortable with temperature. Everyone has got the temperatures, right? Everyone has got the total mass of water that needs to be stored, and that number is between 550 kilograms to about 1000 kilograms, in that range. Yeah, everyone? So, the last bit of step 2 is what I want you to do is start reading from here onwards. That bit. I will just leave this on the screen so you can read it from the screen if you want. Okay? I'm removing the highlight so you can read it clearly. Yeah.
For diameter, you need to calculate it based on the heat flux usage.
Yeah, it's a combination. We need to calculate the size of the tank based on two things. First is definitely that tank should be able to accommodate the total mass you want to store, right? 500, 600, 700, 800, whatever you got. Plus, you want the size in such a way that the diameter and height combination, that the heat loss from the tank to the surroundings is the minimum. So, what we are going to do is in Excel we are going to figure that out. If that was your heat loss, Q dot loss, and that's the diameter, you will get a curve like something like that. And what we want to find is this minimum heat loss condition, the diameter corresponding to that. Once you know that minimum heat loss diameter, you should be able to figure out how much height you need to fit in 500, 600, 700 kilograms, whatever kilograms in there. Make sense logically? So, what you have drawn here, the inner cylinder, the black color cylinder, is the actual tank size, where the volume of water. The outer one, the blue one, is the insulation size. Okay? So, in a 2D plane, it will look something like this. Question says, the tank has an insulation of 12 centimeter on the cylindrical surface as well as top and bottom surface. We don't want any losses. Okay? Now, further it says, not there, here. The heat flux rate as provided by the manufacturer, supplier of that insulation, for that size insulation, 12 centimeter thick insulation, is that with your student number. So that will give you kilowatts every square meter. Now, what is that square meter? Is the total surface area. So, cylindrical surface area and the top and bottom flat surface areas. Total surface area outside. Make sense? So, to find Q loss, you would need that heat flux based on your student number, and then you will need total external area. total external surface area. So that will be circumference times height gives the cylindrical, and pi by 4d square times 2 gives the two surface area, top and bottom surface. Clear? What we need to do is put that in an Excel in a form that it's pointing to two cells, diameter and height cell. So you start changing the diameter, and your target is volume. Your target is your volume. So let me, is that visualization clear for you? So I can clear that up and I can draw a few more, write some kind of a table. So, how much volume we need to store? In my case, is about 839 kilograms, which I need to convert into cubic meters. There is some clause in there. You cannot say a liter is equal to a kilogram.
So storage volume is capacity.
Yes. So, volume, capacity, but in meter cubes, not in kilograms. So, let's say this was 0.8 meter cubes, 800 liters of volume. I'm just making up a number. Okay? And that's the internal, that's that volume in 3D. Okay? So, you have internal diameter, you have internal height, then you have external diameter, external height. The external diameter will be nothing but internal diameter plus 2 times 0.12 because insulation on both sides. Yeah, with me? Say your external height will be internal height plus 2 times 0.12 because of these two. With me? Clear? Yeah. So what we do now, we start. That's constant. That's constant for no matter how many iterative steps you do. So that's constant. Whereas what we want to change is we start changing our diameter. So we start with some upper limit or lower limit. Now go to figure 2 in there and tell me what is the physical limit now. I think figure 1, not figure 2. Figure 1. Yeah, good. There is a small node under figure 1 point something. Insulated tank maximum diameter must not exceed 1.6 meters. So we start with 1.6. But that is our external, not internal, insulated tank. So if external is 1.6, internal will be 1.6 minus 0.24. Okay. So let's start with 1.36. Okay. Is everyone with me? Now we start incrementing. I mean, instead of starting in that odd kind of number, I might start at 3.5 and then increment it 1.30, 1.25, 1.20. Same step, increments. That's just we're doing it manually. Now, if the diameter was that much and the volume must be that much, how much should be the height? You can easily calculate that volume of a cylinder going backwards. Right? I don't think I need to explain you that, all of that. So once you have the height, then you add one more column, which is Q dot loss. So you have the external diameter, external height. Once all of these are filled, you can find the total area. You can multiply with your heat flux based on student number to get your Q loss. And then draw a graph that against external diameter or internal diameter, one of them, whatever you want. And you would get at some point, so you'll have to do this up to maybe 0.3 meters or 0.5 meters. And you would get, it starts, the heat loss starts somewhere high and then goes down and go again high. Then what you're doing is optimization. This is the optimum diameter at which you have got a minimum heat loss. Now in real world, practical, so let's say you come up with a diameter that is, let's say 0.8395 meters. Some number, okay? Somewhere you come up with an optimum, which is such an odd number. Now, practically, can you go and buy a tank of that diameter off the shelf? Can you make one? Would it be wise to make one? Why? Because a custom-made tank will be so expensive. Rather, you would buy something off the shelf. So what, as an engineer, what will be your decision? What will be your recommendation?
Find the nearest
Huh?
commercially
Yeah,
available.
but so which diameter would you select? What would you? 0.9, okay. What about 0.85?
Yes, maybe. If they
So you see, between somewhere there and there, the heat losses are almost the same. So you, based on your data, you have to make a recommendation to me as your senior engineer. You're the junior engineer. You're working. I've given you the project. You have to tell me. I know but I don't have time. I've got 100 projects. I've given you one project. So you tell me. Optimum diameter is this, but within this range is okay. Go and buy anything within 0.8 to 0.9. Whatever is available off the shelf. Wider range you give, more easier or our profit margin can be increased. Once you present that report to me, in real world I would say, okay, I'm happy you've explained this to me, you're making a presentation to me, and I would say, okay, now go and source the material. Go and find the suppliers, get the costs, and let's do the costing of the entire project. Once that costing is ready, then we go to the client and say, okay, it's going to cost you so much with 30% markup. Make sense? Okay, so I've given you extra discussion on the logic behind it, why you should give me a range, not one number. If you just give me one number, I will be very upset as a senior engineer. I will say, why are you increasing my workload? Why are you increasing the extra cost of the project? Logically, you should be giving a range with one number, saying this is the optimum, but it will be difficult to find, hence this is the range within which, okay? So go and fill that table, make a table in your Excel.
So you said don't take 1 kg as 1 meter cube, right? Is it because of temperature or?
Yeah.
So
Density at higher temperature will be lower, right?
Yeah, so which temperature should we be considering for this?
You tell me. You tell me, all of you, as a class, as a team, tell me. Okay, one of your classmates saying 85. I don't know. He might be wrong. I want more students to support you as a group, make a decision. And come to me, and then I will say yes or no based on that. I've only got one vote for right now, one opinion, 85.
Each right, 85.
Okay, there's two opinions. I don't know.
Storage volume, right? Usually you take 1 kg plus 1 meter. But now the density will change because of temperature.
Anyone else wants to support your classmates who are saying 85?
Yeah, 85.
It's not just because some of this.
Because
Okay, because. Tell me the reason.
goes in then comes out should be 80 to 85.
Coming out 80 to 85.
Logically should
Coming
be
out 80 to 85. Going in 85. Okay, but if you design it for 80, what's going to happen? If you say, okay, because of that range, I'm going to make a tank which can accommodate water of that mass we calculated, but at 85 degrees Celsius density. If the temperature goes to 80, anything above 80 is going to expand, and what's going to happen? Practically, what's going to happen? Overflow. Perfect. Good. Start thinking practical. It will overflow. Don't want that. That's a very bad design. Okay, so you're going to design it for 85. Is that clear? Now, what else? What happens? How precisely, how confident are you going to be able to never go above 85? What happens if it goes to 85.5? Sometimes, for some weird reason. Tell me, what are you going to do? Not once it's manufactured, now, while you're designing. Do you need to apply some factor of safety? Okay, apply, and that factor of safety will be extra buffer volume, empty volume at the top of the tank. And each one of you might make some recommendation. How much? 1%, 2%, 10%, 50%, how much extra volume do you want? You tell me. Okay, 5% one of. Who said 90? Someone said 90? 10%? Okay. 20%? Okay. 30? 20%? Okay. Now, larger the empty volume you add, more expensive the tank is going to be. Now, you tell me the reason, who have said 20%, how it will be. You have to sell it to me. Okay? Why 20% is better than someone who has said 5%? Why is it better? And why is 5% better than as compared to 20? Sell it to me. Me as a client, okay? Not as a senior engineer, but as a client. Because you're delivering this system to me. It's going to cost me extra. You're going to charge me extra money. But you have to convince me that it's worth spending that extra money.
Temperature.
Because if your salt production you want to increase the full load, you can get a higher.
Okay, good. So what one of your classmates is suggesting, in future, if I want to increase my capacity of the production, I already have that. Okay, I'll buy it.
Okay.
And you're saying it's only for another $5 or $10 because the project cost is going to be so much. It's only $50 extra or $100 extra. Okay, and why 5%?
I mean, the volume of the water is not going to increase that much. It's not going to overflow more than the 5%.
Okay, so you're saying we're not going to charge you anything extra. We're just giving you 5% buffer. You're not charging. You're not telling me, and your logic is that this customer, me, after 5 years, I'll realize I want to expand my factory and come back to you, and you're going to charge me another $100,000. So you're a cheeky businessman. You want to make more, but that's okay. That's fair. It's his business, right? And he's too generous. He's giving me. But that either of it is, as a client, I will always be happy, right? And none of you are ethically wrong. You're not doing anything ethically wrong. Both of you are doing ethically correct things, technically correct things. Okay. So the reason I'm extending this discussion there is you have to grow as an engineer. You have to start thinking outside the box. All those other things. So now continue and finish this in 5 minutes with the whole table. Yeah, 5 minutes you can finish. No.
So we need to indicate what's our safety factors also.
Yes, right. Saying, and then just one sentence. I'm not going to argue your logic, but if you don't write any logic, no assumption, then I will deduct some marks. Ask him. Ask him. Yeah, sure. Ask him. He's not doing anything. He's waiting for you to finish. I'll be starting with the maximum. Yes, sir. Question is given. Look at the
You can just use the MD factor.
Which one?
The MD, you make your tank right with the volume, hot water, take a safety factor to
Oh.
right, you just use that. Based on this equation,
surface area.
right? Wow.
You done it.
So many page. This private. 10% buffer.
You want to convert mass to volume, right? So what do you need to do? Density of specific volume you have to use. So mass times specific volume will give you volume. What's the unit of specific volume? And that BF, this will be at 85 degrees Celsius. Clear? Mass of water. So let me rewrite that. That's total mass. In kilograms times specific volume of saturated liquid from table A4. Go to table A4. Maybe I'll measure up the applications. So that one there. Any. That will only show that it goes, that's the optimum.
So you say the buffer is only the buffer is only on the temperature, not the.
Yes.
Pressure.
Not the volume, like the buffer is because
Temperature, yeah.
we buffer the temperature, then we get the specific volume a bit higher, then we can get a bit more volume. That's just put 100 degrees.
Because the cap is 85 now. Cannot like.
Cannot be lower than 85.
Yeah, so it can be higher.
Kilograms. Is that volume or kilograms? Okay. Okay. Oh no, not big. To find the sun. Yes, go back to the under of the house. Yeah, 170. Yeah.
The cube per kg.
How do you get the Okay. So you've got the first column of that paper. Now you fill the
The one that we find per hour is a mesh, right?
Yeah, I just say is one day we use this amount.
Oh, so it's the mass of per day lah,
Per
then
day
mass
lah.
per day. Okay.
So I believe it's just this is for one day lah. It's the quantity we use lah. And you go up to the
What time?
7 o'clock.
Wow, very tight.
Back same.
Okay lah, usually like the flight boarding, they need to like, I mean when they like the flight, they also require luggage all this. Should be still time one.
Okay lah, fair lah. I never really fly. I don't fly a lot. So.
Oh, last I also don't really fly. But if the flight is early, then maybe they can come in time.
I don't fly scared. So surprise them.
Oh.
Actually, I thought using density. Thought using density to find the volume. So the density at 5 degree, right? This one. This one is 1 meter cube. Yeah, mass over density.
Yeah, correct. At first I also find like that, but he said need to use specific. Yeah. But it should still come back to the same. Should still come back to the same volume one. I tried. I think it's somewhere around the same. Just now mine was like 699, so this one is, let's say, this a bit more lah, but like 10, 20. Don't be higher than 2 meters. Q loss equals Q. External error.
Quicker guys, because I want to explain you step 3 as well. We won't be able to solve everything, but I will give you a head start. Step 2 everyone will get 100% most likely. If you have written all assumptions and everything is clear, you're not making any mistakes. And then step 3 will be
By the way, the surface area, right? Can you include the what's the
external surface area.
so it's
External surface area. Yes, minimum heat loss.
How you calculate the Q loss again?
Pardon me? I'm adding 1.1, 10%. Okay. But you can do 5%, 2%, 20%, whatever you want. Just provide the justification, like one sentence. Not more than that.
So the volume you add by how many kilos? That's not 5%.
I added 10%. Okay. Now you do whatever you want. That one. No, there's a specific volume. Here. Has anyone got a simplified formula for H? HI equals total volume divided by huh?
I use 4 divided by V2 squared times 5.
But the total volume should be there, right?
Yeah.
And then rewrite that equation. So tell me the rewritten simplified equation. So I don't need to spend any more time. Now, okay, so it becomes 2 pi r squared plus 2 pi r l or height, 2 pi r h, and we want to find h. So volume,
Is that no formula, right? Just anyhow take out.
and we want to
This one
find
is from 1.35 to any number.
so total volume divided by what do you say?
There's no formula.
Let me
No,
read
it's not a
out.
formula.
I thought it's because the limit, limited is 16 to
Yeah, right. So should be the highest should be 1.36. Yeah. This one should be largest should be 1.36. 0.24. I thought you put 3.5. Yeah, height need formula. Height you need to use the volume divided by pi r square.
Something wrong.
Should be volume divided by pi r square.
The I used was the diameter divided by pi d square divided by 4
For
for the height.
can you repeat that?
The volume
Yeah.
divided by pi d square divided by 4.
No, that's not going to give you that height.
Volume.
Oh, then
Volume is
Because it's pi r square
yeah. So you're saying volume divided by pi d square
over 4. Yeah.
Pi
divided by 4.
pi d over 2 square. Should be volume divided by pi d over 2 square.
Yeah.
Yeah,
Pi.
d over 2 square.
So then d should be twice, right? Or
R is divided by 2.
okay, hold on. So let me simplify this. Pi pi r square. Okay, let me use one of your formulas. So that's volume. You're saying divide by
Pi d over 2 square. D over 2 square.
pi times.
You open bracket. You need to open bracket.
Diameter
Divide by 2.
square.
Divide by 2 square. You need to open bracket.
Divide by. Yeah, okay. But there is open bracket.
No, I mean the AC5. AC5, the last one.
Yeah.
Last one. Yeah, this one you need to open bracket, then inside divide by 2, then outside you power of 2.
He says before the AC5.
AC5.
Before the AC5.
Yeah, open bracket.
Then divide by
Then divide by 2. Close bracket.
You're doing it radius.
Yeah.
How was that then? Okay, and you're saying
Power of
radius
2.
square.
Yeah.
One bracket missing. Okay.
missing capacity.
So just let me check whether that's going to give us the right volume. I'm just going to cross check. So equals
0.
Yeah. Surface area.
times h.
Shouldn't your storage be meter square?
Square
Meter cube.
Meter cube.
Yeah.
Storage cube is 0.2 something.
Meter cube. No, meter cube. Yeah, that is a liter.
Okay, good.
Maybe 0.2.
Yeah, yeah.
I was just trying to cross check whether we are getting the right volume because you used radius in there. So now we have got that. So just delete that one out. And we have I'm going to use heat flux as just 0.15. Okay. You're going to use your own student number heat flux. Times in bracket.
2 times pi.
Now you've got 5 times external height times external diameter plus 2 times
Pi.
external diameter squared times 5 divided by 4. Okay.
1 point something.
For me, that minimum or optimum diameter is somewhere there about 1.3, but I'm going to say between 1.2 and 1. Hold on. AE is my x-axis. Okay, diameter is my x-axis. AG is my heat flux. Good. Or heat loss. So let me just add.
Yeah,
Okay, so that's the range.
loss. This is time.
That's the range for me. What are you getting? Anyone wants to share the range or optimal diameter?
1.1 to 1.3.
1.1 to 1.3. Okay. Anyone else? Yeah? Oh, you need help? You're getting lost, right?
Loss in
Which one?
JD loss.
Oh, heat loss.
So,
This one you get heat flux. Yeah, times minus 0.01. You just copy this in.
So 1.4 is fine.
Yeah, then you press equal in front.
So some of you might get 0.8 to 0.95. So anywhere between 0.8 to 1.3 or 1.4 will be within the student marks.
This one the formula very long.
Oh, this one just time external.
Oh,
So this is heat flux.
that's the external damping.
Heat flux constant.
Yeah, correct. So you need to find the surface area for the cylinder. But this one you can get on the video. Because you use like divide by 4 or something, then you get the D, you don't need to divide by 2. But you can use mine first. I send it's the heat flux times 2 pi 2 times pi Pi, then you press that, then times diameter divided by 2
Diameter external.
internal,
Diameter
yeah,
divided by 2.
divided by 2 times height,
Height
then
internal.
yeah, height internal, then plus 2 pi 2 times pi 2, yeah, times diameter divided by 2,
External diameter.
yeah, internal, all is internal.
Okay.
Then you close bracket. Oh, you need to bracket up the diameter divided by 2. Yeah, this one. Then to the power of 2. Yeah, then you enter. Close bracket and enter. Yeah. Yes. Then you just drag everything down. F4. You just press F4. You have F4. Yeah, you show your money side. Wait, undo.
So F4 then enter.
F4 and enter.
You do how many? See you like it's 0.0. Your diameter so little.
Yeah. No, diameter is 1.35.
Right. So you do all the way until.
Yeah, all the way until 3. Although some of them already reach the limit, right? It's just to draw the graph to have more defined.
The limit is which one?
Actually, the limit, right? The limit is cannot exceed. The diameter we won't exceed already because we already used the limit. Then the next limit is the height. So actually, I can use until 0.75 only because I cannot exceed 2 people. But you just need plot all this out, right? So your graph will be nicer. You just drag down. You highlight everything, right? Then you drag down. Yeah, until 0.3. And this one I think you just all can just copy down. So now you use the insert, you highlight the last one, then you control, then you highlight the diameter. Yeah, I think I highlight wrong. Yeah.
Maybe bracket is missing somewhere. Check the bracket. So it between. Maybe you can read it from. Yes. And why have you gone to the smaller diameter? What's the single diameter? Go down to 0.5. So you will
Yeah,
the
now
dark
we-
band.
So okay, so the cap.
Yeah.
So the cap is basically 1.6.
Yeah. So you will reach already. Yeah. No, 1.6 is on the
I
external.
don't know what the rules here.
Oh yeah, this is correct. Yeah.
We only have till 6.
1.6.
So this one is until
If you're happy,
0.75.
I'm
Yeah.
happy.
Yeah. So your gap is only like
Is the gap.
Next 20 minutes.
Usable and usable.
yeah. So anything I
Huh? Shit, that's what I'm going to I think you not him this sorry. I WhatsApp you.
Is that diameter or? So why you start
I go first. I help him.
Then the description 1.6. The internal cannot be more than 1.6. go to 1.33, let's say 33. Yeah, 1.33.
Curve is better now.
Airport.
Just 0.1. We will continue for another 10-15 minutes, although it's 6 o'clock. I'm planning to help you with step 3. So if you can hang around, don't leave. Or you've got work. Okay. So if someone else can help. They will. Keep going down 4.1. So, cylinder area or the black area is probably okay, guys. 1 more minute and you finish. Yeah, that's all. How about we do this? Next 10 minutes, I explain you step 3. And then if anyone wants to leave, they can. And then another 10 minutes, I can stay and finish the tank sizing for anyone who is struggling. Okay? So that way, we are not making students who are finished tank sizing just wait and waste their time. Fair? Everyone pay attention. Yeah, sending someone else. Okay, yeah, or someone will record. Yes. Okay, what I want you to do, open lecture notes from week 7. Week 7, is it? Or week 7? Yeah, week 7.
Only question.
And we can also go and open week 8 just to help us fast track things. Also, maybe we can go to week 9 or a week 10 tutorial. So, week 7, week 8 lecture, week 10 tutorial. Because all the equations are there. Week 10 tutorial solution. Week 7 notes. Week 8 notes. Okay. While they're opening, I'll start explaining. So most of you have finished that part. Now we start with exergy analysis. In exergy analysis, step 1, it's quite straightforward. That one there. And we can do that right now, which is it's asking you to determine the exergy that is applied into diesel generator with the combustion of air and diesel mixture in kilowatts for every hour from 8 a.m. to 5 p.m. Assume complete combustion of the diesel. Now, that will be as simple as multiplying mass flow rate of the diesel fuel times calorific value, and the calorific value is given up here, 45,000. So, have you already calculated volume flow rate of fuel? Do you know, can you find volume flow of fuel, diesel going in? How much volume is being consumed of diesel? We have done that. I'll show you where in the Excel. Sheet 2. You have to make similar kind of code. You have to make similar graph for fuel consumption and load. Okay? And then use the equation from the graph from fuel consumption and load to find fuel consumption for every hour. Is that clear? I mean, is it easy to do that? How? I mean, are you serious or are you just joking? I'm not very sure. If you're serious, I can show you. Yeah. If you're just joking, mocking me, then I'm not going to show you. Yeah. Use the formula. I'll just delete that, okay? For now, because they're just interfering. Delete that for now. You don't delete yours, okay? Can someone go and check in the catalog what was the unit? It was liters per hour, right? For fuel? Per minute or per hour? Okay, so that's correct. So now we need to convert that liter per hour to kilograms per second. Times specific gravity of diesel, which is given in the question. Diesel, assume that specific gravity of diesel to be 0.85. Times, not times, divided by 3600. That becomes your mass flow rate of diesel. Clear? Good. So, going back. Liters per hour to kilograms per second. So, first we convert liters to kilograms by multiplying with specific gravity, and divide by 3600 gives us per second. Okay? Now I'm going to minimize that and explain you. So step 1, to find that, what you do is m dot fuel times calorific value of 45,000 kilojoules every kilogram, and that's kilograms every second. Whatever number you get will be kilojoules per second, which is nothing but kilowatt. And that's what it's asking. Find the exergy of diesel assuming 100% combustion in kilowatts. Simple. just multiplication of mass flow rate times calorific value. So that's dot point 1. Dot point 2 always is getting a little involved. So determine the exergy of exhaust gases before they enter the heat recovery heat exchanger every hour. So everyone is now familiar with T1, T2, T3 temperature. That's the water temperature. Coolant going in, coolant coming out, 85, 35. Exhaust going in, 455. Exhaust coming out at whatever that exhaust temperature is. This dot point is asking you to find exergy at that point. So let's call it T exhaust in. So we want to find X E exhaust in. Now X E dot exhaust in. Okay. Now for any exergy estimate, if you want to find any exergy, either for exhaust, either for coolant, equation that you are going to use is from week 7 lecture. For open system, let's look at one of the equations here. So we are going to use that equation, point 1 in. Let me zoom in and it will be a lot clearer. That equation there, that's the flow exergy at the inlet multiplied by the mass flow rate. Okay? So we will do to find the exhaust exergy. Mass flow rate of exhaust. Do you know already mass flow rate of exhaust? Step 2, you have already calculated mass flow rate of exhaust. Times small x ex, so xef, that equation. So I'm going to write that equation up in bracket. H in minus H0. What is H0? Is the dead state. What is the dead state? Is given as in the question. Do you remember what's the dead state? No? Don't remember? That's the dead state. 20 degrees and 100.3. So that edge is at 20 degrees. Okay, so let me add different brackets. Square bracket there, round bracket here, and then T0, so minus T0, that's the dead state temperature. So what temperature are you going to use here?
20 degree.
20 plus 273.
273.
Yes, in kelvins. Always in kelvins, that one. Okay. Times entropy at point 1 or inlet. What's the inlet temperature? 455. Minus dead state, which is at 20 degrees. And then, if you read the question carefully, assignment question, do you remember what the question says about kinetic and potential energies? Negligible. So that part is gone. That's the end of the equation. Okay, so that's the general equation for any point. If you want to find exergy at that point, that's the equation. If you want to find the exergy at that point, still that's the equation. Instead of exhaust, it will be coolant. Okay, make sense to everyone? So if you want to find x E dot coolant in, same equation, logic, just that exhaust in becomes coolant in, mass flow rate becomes coolant mass flow rate, and all of these for coolant as well. Now, how do you find change in enthalpy and change in entropy? Because temperature T0 is known, is 20 plus 273. That's easy. The flow rates are known already, most of them. The only trick is that and that. If you know how to find that, the problem is solved. So let's look at change in enthalpy. Do you remember the equation for change in enthalpy? It's a single phase fluid. Coolant is liquid, completely liquid, it doesn't boil. Exhaust is gas, it doesn't condense into liquid, it stays gas. So it's Cp delta T or Cp T in minus T out or T0. In this case you want in minus 0. So what is temperature at inlet? 455 minus, what's the dead state temperature? 20. What's the specific heat capacity of exhaust? Let me put this back to exhaust. So it will make it exhaust in. What's the Cp of exhaust? 1.005. And that gives you delta H. Simple. Clear? Now, if this was for coolant, what are you going to do here? This is stays the same for coolant, but what temperature will be for coolant? What will be the in temperature? 85. Dead state, still 20. What will the Cp of coolant? We are assuming it to be same as water, 4.18. Simple. Now, change in entropy. Change in entropy, we have studied that. Here, that kind of equation or that equation. So I'm just trying to find a simpler version of it. Here. Let me open week 6 lecture. Week 4. In week 5 lecture notes, we have gone through how to find change in entropy for gases and for liquids. And if you remember, there is a natural log equation. Cp natural log of T2 over T1 minus R natural log of P2 over P1. That equation we have to use for change in entropy. For exhaust, we are going to use that. So, change in entropy, S in minus S0, okay? What we want to find is S in minus S0. We are going to say Cp exhaust, and that's for exhaust, okay? Times natural log of T in over T0 minus R exhaust natural log of P in over P0. That's it. Now, further in the assignment, what is said? What happens to the pressure within the heat exchanger when the exhaust goes from in to out? What's the pressure here and what's the pressure here? Pressure losses are negligible. So P1, P in is equal to P0. 1. Natural log of 1 is 0. For coolant, for water, for exhaust, that term will disappear always. So your change in entropy is nothing but that much. The only thing what you have to remember, temperature should be in kelvins. That's the biggest mistake students will make. That's it. That's the entire entropy, exergy. Once you know each one of those exergies, and then if you go through the questions, so determine the exergy of exhaust, determine the exergy of coolant. After that, you go determine the exergy destruction. Now for exergy destruction, you're going week 7. That equation. Okay? So, we want to find exergy destruction in the generator. So, I'm going to redraw something. Is it okay if I erase that part? Okay. That's your diesel generator. What's going into the diesel generator is fuel plus air. Question already says ignore any exergy that air is bringing in because air is already at dead state. So there's only the exergy coming from fuel. Have you already calculated exergy from fuel? Step 1, which is mass flow rate of fuel times the calorific value, which I showed you just before when we calculated the mass flow rate of diesel. So exergy is going in. Some of the exergy is going out as electrical power. Some exergy is going out in exhaust. Which is that? The exergy that I showed you the equation for that. Some exergy is going out in coolant, which I showed you as well, right? That exergy. Some exergy is going back in form of coolant from there. Which same logic, same equation you can find. But for 35, not 85. So that should be 35 minus 20. Okay? So that basically is what is going in, what's coming out. There is one more which is coming out, which is Q dot radiation. Yesterday we were calculating, we have already done that, right? Q dot radiation. So, equation is there. In that equation, exergy that is going in by mass, so that sum will be exergy by fuel going in into that box, into that block. What is going in? Fuel is going in. What else is going in? Coolant at 35 is going in. Coolant at 35 returning because coolant is cycling. Make sense? So that is two parts. Fuel going in, coolant going in. What is going out? In form of mass. Exhaust is going out, coolant is going out at 85. So that captures that part. Now, are we getting any work out from the box? Yes, electrical work out. Do you already have the total electrical output? You have. Now, are we losing any heat exertion form of heat. Radiation. Do you know the radiation heat? So that Q dot B will be your radiation kilowatts. Do you know that?
Yeah.
You will be able to find yesterday we discussed using the graphs again. Radiation heat loss. In there, do you know the dead state temperature? Yes, 20 plus 273. Now, do you know the boundary temperature at which radiation is happening? Open the catalog, please. Everyone, look at the catalog. I have the catalog here. Radiation heat loss, surface temperature, 364. So that 364 is your other temperature in that equation. So 20 plus 273 divided by 364. Can you find that then? Easy. Is that clear? So once you substitute, you know this, you know the electrical, you know the fuel and coolant going in, you know the exhaust and coolant at 85 going out. This is the unknown. Find the destruction. Remember, destruction can never be negative. Has to be positive. If you are getting negative, then you're messing something up with the signs or something. That's the only trick. Clear? I know it's a little bit overwhelming, but try your best. Now, the assignment is also due on 31st of July. What I will try to do, maybe organize an online team session for half an hour something in 2 weeks time, maybe, or 1 week time. Yeah, I will do that. But what I want from you is everyone should have tried. I cannot be explaining everything again. I will help you with specific questions. I'm stuck here. Which equation? I'm getting a negative answer. Why? Don't come to me. Can you explain me everything? I'll go tired. Okay. Basically, you find destruction, then you find a cost. Costing will be easy. It's not that difficult costing wise. Maybe have a look at week 9 lecture notes for costing. Owning the diesel generator, then you continue and owning the heat exchanger and the electrical output, all of that is costing. So that is captured in, not here, week 9. And week 10 basically tutorial. Maybe week 11 tutorial, sorry. From here. It wasn't here, sorry. Okay, I'm confusing myself. Here, that's the costing. So if you watch that 1 hour video, costing will be very clear. Please watch that video. That's from week 8 part 2 video, 1 hour. That will, the entire rest of the costing will be clear. So do that over next 1 week or week and a half, and I'll see when I can fit, because as soon as I go back to Melbourne in 5 days, so next Monday Melbourne semester starts, and I'm teaching 2 courses, one with 450 students. That's crazy. I'm teaching like almost 16 hours every week face to face. 16 hours every week face to face. That's going very crazy. And I've got 14 PhD students and 30 capstone students, 4th year project students to supervise. So The only thing is I don't lose my interest.